Hello, I'm Daniel Reid and I'm from the School of Mathematics at the University of Leeds, and I'm going to talk to you today about differential equations and just give you a general introduction to the subject of differential equations. The first thing I'm going to say is a little bit about why you might want to use differential equations. I'll say a little bit about formulating differential equations. That's something that you often get asked to do as part of your exam questions, and what you definitely do get asked a lot in your exam questions is how to solve them. And I'll give you an introduction to at least one method for doing that during this podcast. So very quickly, why might you want to use differential equations? Well, differential equations are used throughout the sciences and technology and financial modelling. Basically, differential equations get used wherever there's some quantity which is changing with respect to time or space. And that's because, as you know, differentiation is about finding rates of change. So if you have one quantity, let's call it y, which is changing with respect to another quantity, let's call it x, then the graph will look like that. The differential, differentiating y with respect to x, tells you how fast y is changing with respect to x. Now, because many physical laws are formulated in terms of the rate of change of something with respect to something else is equal to something, differential equations get used all over the place. So the first thing you want to do is you want to formulate your differential equation. You want to decide what is the physical law I'm trying to write down, and then you want to go ahead and solve them. So the first thing I'm going to do is I'm going to go through just a few examples from the physical sciences and from other sciences where differential equations get used, just to give you a flavour of different areas where this subject comes in. So the first three areas I'm going to talk about very quickly are all from the area of physics. Actually, my background is in physics, so this is what I know best. The first one I'm going to talk about is radioactive decay. And in radioactive decay, what you have is you have a whole load of atoms. Let's call them N atoms. And all the way around there. And they decay. They decay into another state. So basically, they disappear one by one in a random way. And the rate of change of number of atoms is proportional to the number of atoms. Now, as the atoms decay, the number of atoms is decreasing. And so what we have is dN by dt, that's the rate of change of number of atoms, is equal to, because it's decreasing we need a minus sign, because it's a proportional relationship we need a proportionality constant, and it's proportional to the number of atoms n. So there's a very simple differential equation which we can formulate from just a simple insight that the rate of change of number of atoms is proportional to the number of atoms. So there's our differential equation. And then, having got the differential equation, you'd go ahead and solve it. And I'm not going to go through the details of solving it now, but the solution looks like n is equal to n0 e to the minus k times t. And in terms of a graph, what does that look like? That looks like that, where the number of atoms n is basically decreasing as the time increases. And the first thing you should see is that the initial number of atoms is n0. This is an example of an integration constant or an initial condition. Every time you solve a differential equation, you'll find that there are integration constants or free constants that you need to determine, usually from something like the initial conditions. So that's our first example of there being such an initial condition. Okay, so the second example that I'm going to talk about is circuits or electronics. And a very simple example of that, let's think of a simple circuit which involves something called a capacitor. So here's the symbol for a capacitor, and it's in a circuit with a resistor R and a battery here. And The battery you would say has a voltage V, and the capacitor has a capacitance C. And there's a relationship between the capacitance and the charge stored on the capacitor and the voltage. And that relationship says that the voltage across the capacitor, let's call that V subscript C, is equal to the charge Q on the capacitor divided by the capacitance. So where does the rate of change come in here? Well, this battery here drives a current around the circuit. So let's give that a symbol I for the current. And the rate of change of charge on the capacitor is just the current flowing in the circuit. So we can go straight to saying dq by dt, the rate of change of charge on the capacitor, is just equal to the current I. Well, that's not yet a full differential equation, because what we'd like to do is we'd like to relate the rate of change of charge on the capacitor to the charge that is actually on the capacitor. So we need to relate the current to the voltages that are going on in the system. So again, actually the current flowing in the capacitor is just the difference in voltage between the battery and the capacitor divided by the resistance. So that's V minus the voltage in the capacitor divided by the resistance. And we know that the voltage in the capacitor is just Q divided by C. So that's the voltage in the battery minus Q over C divided by R. So all of these are different constants. So the voltage in the battery, the constant which is the resistor, the constant which is the capacitor. But what we have now is a differential equation which relates the rate of change of charge in the capacitor to the charge stored in the capacitor. What does a solution of that look like? Well, what you'll find is that the charge increases with time up to a maximum where it's fully charged, and actually the time it takes for this to happen you can work out because there's a capacitance here and a resistance R here, and it's actually the product R times C, which turns out to give you the charge stored, the time it takes for the charge to reach its maximum typically in the capacitor. So this line here would again be the solution of this differential equation. The third example from physics is from Newton's second law. And what is Newton's second law? Newton's second law tells you about if you've got a mass, let's call it m, and it's got some forces on it, what is the acceleration of that mass? And its force is equal to mass times acceleration. Well, that's not yet looking like a differential equation, but the acceleration is related to the rate of change of something. So the acceleration is actually the rate of change of velocity with time, and since the velocity is the rate of change of position with time, the acceleration is actually the second derivative of position with respect to time. So that's the acceleration, and that's got to equal the force divided by the mass. So if you know what the force is, this here is now a second order differential equation for the position of this mass with respect to time. So for example, a very simple example, if this mass is attached to a spring, then the force on the mass is actually equal to minus the spring constant k times x. So we end up with d2x by dt squared is equal to minus k divided by m times x. So this then is a second order differential equation saying something about the rate of change of position of the particle with respect to time. And again, I'm not going to go through the detailed solution of that. In fact, I believe that this is going to be treated in another podcast. But what's it look like? Well, you perhaps know that if you've got a mass on a spring, it tends to oscillate with respect to time. So solutions to this differential equation look like x is oscillating with respect to time. And actually the mathematical solution is that x is equal to a cos omega t plus b sine omega t, where omega is equal to the square root of k divided by m. Because this is a second order differential equation, its solution actually requires you to integrate twice effectively. And you can see that there are actually two integration constants here, a and b.